Welcome back to Calculus 3. I'm Dr. Jeff Groh, and this is your Exam 2 review. In problem 1, I ask you to evaluate the following limits. If a limit does not exist, explain why. On the first limit, we have the limit as xy goes to the point 1, 2. The function is 5x squared plus y squared over x squared minus 2y squared. As you can see, we have a rational function, and if we plot the point 1, 2 in the denominator, we do not get 0. Under these circumstances, we can evaluate the limit by simple function evaluation. That gives us 5 times 1 squared plus 2 squared over 1 squared minus 2 times 2 squared. 2 squared is 4 plus 5 is 9. And we have 1 minus 8, that's negative 7. On the second problem, we have the limit as xy goes to 0, 0 of exactly the same expression. If you attempt to plug 0, 0 into both the numerator and the denominator, you get 0 divided by 0, and that means, in the context of limits, more work. So on path 1, we might select r of t equal to t0. Taking the limit as t goes to 0, we'll have 5t squared plus 0 over t squared minus 0. The limit is, of course, 5. On path 2, we might follow the other axis, 0t, and take the limit as t goes to 0 of 0 plus t squared over 0 minus 2 t squared, and get a limit of minus 1/2. It follows then that the above limit does not exist. On problem 2, I ask you to calculate both dz dx and dz dy on the following functions. And on the first one, I have x minus y over x plus y. Because we're dealing with a quotient, to calculate these partial derivatives, you need to use the quotient rule. Yes, all the way back in Cal 1, you learned that the derivative of the quotient is the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. So in calculating dz dx, derivative of the top is 1 times the bottom minus the top times the derivative of the bottom divided by squared. This simplifies as 2y divided by x plus y squared. dz dy is the derivative of the top times the bottom minus the top times the derivative of the bottom divided by the bottom squared. The y's will cancel this time. We'll have minus 2x divided by the quantity x plus y, quantity squared. On part B of problem 2, I give you z equals x to the power of 3/4 times the inverse tangent of x squared y. To calculate dz dx, we have to use the product rule. So the derivative of the first, that just uses the power rule, times the second, plus the first times the derivative of the second. The derivative of arctan, that's the 1. the one I wanted you to remember. That's going to be 1 over 1 plus whatever you have in the function squared, and then times the derivative of the inside with respect to x. Whatever you do on the exam, please do not simplify this. Leave it. The partial derivative of z with respect to y does not require the product rule because the first factor is a function of x. We'll have x to the 3/4 times 1 over 1 plus the function value squared times the derivative of the inside with respect to y. Leave that. On problem 3, I ask you to calculate fxx, fyy, and fxy, where the function is e to the 2x sine of 3y. Let's calculate fx first. That's going to be 2 e to the 2x sine of 3y. And fy is going to be 3 e to the 2x cosine of 3y. It follows then that fxx will be 4 e to the 2x sine of 3y. fxy will be the derivative with respect to y of fx. That's going to be 6 e to the 2x cosine 3y, and then fyy will be the derivative of fy with respect to y. That's going to be minus 9 e to the 2x sine of 3y. On problem 4, I ask you to calculate dz dx, where z is equal to 5u squared v squared minus 2v. U is x y squared, and v is x plus y. And I ask you to do this by the chain rule. dz dx is dz du du dx plus dz dv dv dx. dz du is 10u v squared, the derivative of the 2v being 0 with respect to u, times du dx plus dz dv, that's going to be 10 u squared v minus 2 times dv dx. Making the necessary substitutions, we have 10u v squared times du dx plus 10u squared v minus 2 times dv dx. Please, on the exam, do not simplify your answer. On problem 5, I ask you to find the directional derivative evaluated at the point 2, 3. The function in question is x squared plus 3xy plus 4y squared, and the unit vector giving the direction is root 3 over 2, 1/2. As you'll recall, the directional derivative is the gradient dotted with the directional vector. So the first step is to calculate the gradient. The gradient has coordinates equal to the partial derivatives. The partial derivative of f with respect to x is 2x plus 3y. Then, comma, the partial derivative with respect to y is 3x plus 8y. We need to evaluate this at the point in question. When x is 2 and y is 3, we'll have 4 plus 9. And then when x is 2, we have 6. Y is 3, 24. 24 and 3 is 30. The directional derivative then, evaluated at 2, 3, is the gradient dotted with the unit vector. We have 13 root 3 over 2 plus 15. On problem 6, I ask you to find the direction that the function z equals x squared plus 3y squared increases most rapidly at the point 2, 3. A function increases most rapidly in the direction of the gradient. So the gradient is going to be 2x, 6y, and we're going to evaluate that gradient at the point 2, 3. So I'll say in the direction of the vector 418. On problem 7, I ask you to find the equation of the tangent plane of the surface x squared plus y squared minus z squared equals 1 at the point 1, 2, 2. Do you know what kind of surface this is? It's equal to 1, and it has only one negative. It must be a hyperboloid of one sheet, opening around the z-axis. I'm asking you to find the equation of the tangent line at some point. Tangent plane at some point. I'm asking you to find the equation of the tangent plane at some point. So, this is a level surface. The gradient, if we call this some function f, the gradient is 2x, 2y, negative 2z, and the gradient will be normal to the level surface. If we evaluate that at the point 1, 2, 2, we will have our normal vector. At 1, 2, 2, we'll have 2, 4, negative 4. Actually, I'm going to take my normal vector to be a rescaling of this. It'll be the vector 1, 2, negative 2, and I will use this as my point. The equation of the tangent plane then will be 1 times x minus 1 plus 2 times y minus 2 minus 2 times z minus 2, using the formula 0 equals n dot x minus x naught, where x naught are the coordinates of the given point, and n is the normal vector. On problem 8, I ask, suppose that a model rocket is launched vertically and observed from a point 200 feet from the launch site. At apogee, the angle of elevation is 63 degrees. There's a maximum error in the distance of plus or minus 20 feet, and for the angle of elevation plus or minus 5 degrees. I want you to find the maximum relative error. If we define the height to be h, then as you know, h is the distance times the tangent of the angle of elevation. The error in h will be, take the derivative with respect to d and multiply by the differential in d. Take the derivative with respect to theta and multiply by the differential in theta. Then, to find the relative error, you divide both sides by h, but h is d tan theta. plugging these various values in, the error in D could be 20 feet. D was 200 feet. Theta was 63 degrees. And the error in theta was 5 degrees, but that must be converted to radians. So we have 5 pi over 180. Box it. You're done. On problem 9, I ask you to classify the critical points of the following function. It is 2x cubed minus 9x squared plus 12x plus 2y cubed minus 6y squared minus 18y. First, we have to find the critical points, and since this is a polynomial, all we have to do is calculate the partial derivatives, set it equal to 0, and solve for x and y. Taking the derivative with respect to x, we'll have 6x squared minus 18x plus 12. Note that the other terms have derivatives equal to 0 with respect to x, and each of these terms has a common factor of 6. The quadratic x squared minus 3x plus 2 factors as x minus 2, x minus 1. If all of this equals 0, then by the zero product theorem, we deduce that either x is equal to 1 or x is equal to 2. There's an or statement in there. But between those two, we also have an and statement. The derivative with respect to y must be 0 as well. Taking the derivative with respect to y, the first three terms have derivatives equal to 0. Continuing, we'll have 6y squared minus 12y minus 18. Again, each term is divisible by 6. So we'll factor 6 out. Y squared minus 2y minus 3. We'll factor this as y minus 3, y plus 1. They must have opposite signs and add up to negative 2. We obtain then y equals minus 1 or y equals 3. So we have 1 or 2 for the x and minus 1 or 3 on the y. So if x is equal to 1, we could have y equals minus 1 or y equals 3. On the other hand, if x is equal to 2, we could have y equals minus 1 or y equal to 3. This gives us 4 critical points that we must classify. To classify these, we must have the discriminant fxx, fyy minus fxy squared. So we need to calculate the second order partials. First, fxx. That will be 12x minus 18. Fyy will be 12y minus 12. And fxy, the derivative of fx with respect to y, will be 0. The discriminant is then, and for purposes of our calculations, it might be easier if we factor these as much as we can. A 6 can come out of here and a 12 out of here. 6 times 12 is 72. We'll have 2x minus 3 and y minus 1. Minus 0 squared, of course. The discriminant evaluated at 1 minus 1. 72. 2 times 1 is 2, minus 3 is negative 1. Negative 1 minus 1 is minus 2. Negative 1 times minus 2 is positive 2. We get positive 72 times 2, or 144. That is positive, which means that we have concavity being the same in both principal directions, this will have either a max or a min. We only need to determine which one. We only have to evaluate one of these partials, fxx or fyy, at the critical point. If we evaluate fxx with x equals 1, we'll have minus 6. We have concave down in that direction, and hence concave down in all directions, and that implies that we have a relative max. Now let's do the same for the point 1, 3. Evaluating at x equals 1, y equals 3, we still have negative 1 here, but 2 here. This gives us negative 144. That means the concavity is different in each of the principal directions so that we have a saddle point. How about at 2 minus 1? 2 times 2 is 4, minus 3 is positive 1. Negative 1 minus 1 is negative 2 times 72 is negative 144. Again, we have a saddle point, and that leaves only the point 2, 3 to analyze. De-evaluate at 2, 3. 2 times 2 is 4, minus 3 is 1. 3 minus 1 is 2, we end up with a positive 144, which means we have either a max or a min. Evaluating fxx at 2, 3, we have 24 minus 18. That's going to be 6, which is positive. Concave up in that direction, and hence concave up in all directions, and therefore we have a relative min. This leaves us only with problem 10, where I ask you to find the minimum value of the function f of xy equals x squared plus y squared, subject to the constraint x plus y equals 1. You can see that we have ourselves an elliptic paraboloid and a line, which will trace out a path on the elliptic paraboloid. There should be a minimum, but no maximum. To solve this problem, we first start by writing out h, which is f minus lambda g. That's going to be x squared plus y squared minus lambda times x plus y minus 1. And technically, you don't need to write the minus 1. Our theorem said that the solution to the constrained optimization problem will be a critical point of this function h. By the way, as a critical point of the function h, the solutions to the constrained optimization problems usually end up being saddle points. Go figure. Here we'll have 2x minus lambda, 2y minus lambda, that's 2 equations and 3 unknowns. To these we add x plus y equals 1 as the third equation. Eliminating lambda from the first 2 equations, we end up with x equals y. If x equals y in the next constraint, we have x plus x equals 1 or x equals 1/2. That implies that y is also 1/2, so we have only one critical point. 1/2, 1/2. The value of the objective function here, the objective function being z equals x squared plus y squared, is 1/4 plus 1/4, or 1/2. That is the minimum value